All right, I think it's 2:02 and we can get started. And some people, they are very last minute. So I'm sure there are more people coming. So hello everyone, welcome to ASIC seminar series. And this is John, the seminar coordinator. And together with me is Miss Kathy Medley. Kathy and I will be today's moderator. And our associate director, Ralph Ferrero, also join us, and he will be introducing the speaker. And just so you know that our seminar is being recorded and the video will be later published on our YouTube channel. So please feel free to check it out. And today we are very excited to have our speaker joining us from Penn State. And before he gets started, I will hand this over to Ralph. And Ralph, please go ahead.
Yes, yeah, thanks, John. Yeah, so we have Matthew I'm going to probably say it wrong, Kumjian.
Close enough. Yeah, Kumjian. Yeah.
Kumjian, okay. He's an associate professor at Penn State University, and you did a little bio search. So you got his degrees at University of Oklahoma, and he's been at Penn State for the last several years, and his focus is on mesoscale meteorology and severe weather. I think sounds like he researches all the things that a lot of us meteorologists wish we did at some point in our career. And he's also recently won an award, early career award from the American Meteorological Society, where he's editor and involved with a couple of journals there. And again, his focus is on cloud physics and radar meteorology, and we're going to learn a lot about hail from him today. So I'm going to turn it over to Matthew.
All right. Thank you, Ralph. And thank you, John and Kazi, for helping organize all of this today. And thank you very much for the invitation here, and to all of you for taking some time out of your afternoon to come hear a little bit about hail. So first off, I'd like to thank the collaborators that I've had on this work. And so Kelly Lombardo at Penn State here, Hu Julin, Scott, and Rob are all former or current PhD students of mine. And Joshua Soderholm, you'll see his name pop up a few times towards the end, another collaborator of mine on this work. And so without their efforts, a lot of what I'm going to show today is not going to be possible. So we'll go ahead and jump in. Besides being exciting and interesting, as Ralph was talking about, why should we study hail? So one of the sort of interesting factoids about hail that not many people know is that it's actually the most costly hazard from severe convective storms. And current estimates are something on the order of 20 billion US dollars in damage annually. And so if you take a look from NOAA's the National Centers for Environmental Information, you can look at their $1 billion disaster webpage. And this is just the cost of severe storms over the last 40 years or so. And so the red line here shows that the actual cost of these severe storms. You can see the cost in billions here on the right axis. And over the past 5 years or so, it's definitely been averaging in this close to $28 billion. And this is almost entirely driven by hail. There's a few years in here with tornado outbreaks where there's will also contribute, but the frequency of hailstorms, nickel and dimes the insurance industry, no pun intended, for all these types of damages. So in addition to the economic impacts, it's also a forecasting and operational meteorological challenge. So the typical, common forecast parameters, things that meteorologists will look at to assess the environmental, whether it's conducive for severe storms, things like the convective available potential energy, or CAPE, the vertical wind shear. There's even sort of parameters specially made for hail, like the large hail parameter. They do not do a good job at discriminating or forecasting hail size as well. There's a whole number of studies that can look into this. Here's one of the recent ones from Mateusz Tazarek and collaborators in the Journal of Climate. And I've sort of just blacked out some of the other areas here. They looked at all severe storms, but if you just focus on the hail, down here on the x-axis, you'll see the hail size bins, so less than 2 centimeters, 2 to 5, 5 to 8, greater than 8. And then these are box plots showing the distribution of mixed layer CAPE values and 0 to 6 kilometer shear, both in the European Union in the kind of bluish color, and in the USA in the red color. And although you'll see that as you go up in hail size category, there's a general increase in both CAPE and shear, the sort of discriminatory power of these, or the statistical power behind these forecast parameters is not particularly good. There's a lot of overlap with those distributions. So those typical forecast parameters don't really do much in terms of forecasting help. Further, the hail reports databases that we have both in US and abroad, to put it kindly, they leave much to be desired. And just to show an example, this is from a published paper by Scott Blair in the journal Weather and Forecasting, showing a case happened in Oklahoma. These are NOAA storm reports, which you might find in the storm reports database. There's actually 11 or so on here, and that's more than you'll typically get for a given hailstorm. And so if you're looking at the distribution, you see it's kind of sparse, kind of see some tendency to be biased towards where the population centers are. And the maximum size you see is only, say, 3.5 to 4 inches for these storm reports. But it turns out that this particular storm was well sampled by a field project at the time. And so when I flip to the next image, you'll see what the field project actually found in terms of hail sizes. And so you see a much denser array. This is like a dream if you're a hail scientist to get this type of reports, but this never happens outside of field projects. But what you do notice is that the maximum size found was actually over 5 inches. Turns out this was the state record hail event that would have been missed if we just looked at the hail records. So there's a lot of gaps and biases in our hail reports. And then the forecasting challenge continues with both the sort of short-term forecast and also the warnings once the storm is actually present. They tend to consistently underestimate the maximum hail sizes. And so another study by Scott Blair and collaborators in 2011. This shows the Storm Prediction Center watches. So this is the sort of several hours out type of forecast that's put out by the Storm Prediction Center. The red bars here kind of represent the forecasted maximum hail size in inches, as you see on the y-axis. And then the blue bars here are the actual sizes reported. These are all for what are called giant hail greater than about 4 inches or greater than 10 centimeters in maximum dimension. And if you look at the warnings that were put out, this is when there is a storm occurring. And so these are going to be generally less than 1 hour kind of lead time warnings from the National Weather Service. You see, again, a big discrepancy between the size indicated in the warning and the actual size that was observed on those cases. So these forecasts are based partly on environmental cues. And so that's one aspect we'll be talking about today. And then these warnings are generally based both on environmental cues, but then also when you see the storm on radar. And so we'll talk a little bit towards the end about some of the radar issues as well. So when it comes to studying hail, what are our main science goals? And so our group is basically tackling 3 different aspects of the hail problem. The first is just to better understand the fundamental physics, the hail formation and growth processes. We have a very good understanding of the basics, but then when it gets to some of the details, that's really where we're trying to push the envelope. We also want to try to elucidate those environmental conditions. What are the sort of environmental controls on hail production to try to maybe improve those forecast parameters to have better performance? But then also the internal storm controls on hail production so that we can try to understand storm behaviors or structural features that may be conducive to producing more or less hail. And then finally is to improve the radar-based hail detection and quantification. I put quantification here to imply whether it's sizing or some sort of other impacts-based quantification using the radar data quantitatively to try to understand what's going on. And there's obvious forecast benefits and interest in these aspects, but I'd also say from the economic side too, there's a lot of private companies out there that try to use radar-based sort of hail swath techniques, and there's a lot of challenges with that, which we can talk about later if you're interested. So first, I figured we would just kind of go over a little bit of how do you make a hailstone? How does a storm create a hailstone in the first place? So my stepdaughter loves to bake, so I kind of like to think about it in terms of ingredients, like you're going to try to bake a cake or bake some cookies or something like that. So the first of the key ingredients is a strong updraft. So hailstones come out of deep convective storms, deep convective clouds, kind of like the one shown here. And you need a sufficiently strong updraft to support that hailstone as it's growing. If the updrafts are too weak, then you just won't get hail of any sort of appreciable size to fall out. So you need a strong updraft. One of the key ingredients is actually supercooled liquid water. So this is liquid water that exists in a liquid state at temperatures below 0 degrees Celsius. And in particular, the hail growth region is often cited to be something like -10 to -30 degrees Celsius. So supercooled liquid water drops mainly in the terms of cloud droplets, but also to some extent raindrops we found. They tend to be the source of mass for growing hailstones. So to create a hailstone, it's grown by the collection of this supercooled liquid water. And I have a picture here. This is not of hail, obviously, but this is from a freezing rainstorm we had on campus a few years back. But it's the same kind of idea. The freezing rain happens when raindrops or melted snowflakes into liquid droplets fall into a layer of air in which the temperature is below 0 degrees Celsius. It's stable in the sort of metastable state when it's in the supercooled state, but as soon as it makes contact with that cold surface or with other ice, it will freeze on contact. And so the supercooled drops that come into contact with a growing hailstone can freeze and become incorporated into the growing stone's mass. Third main ingredient we need is a collector particle, which we call an embryo. Typically, these are things like grapple, which we see sometimes here in the winter. I kind of like to say they look like little Dippin' Dots or little styrofoam balls. You see them kind of bounce around and you can squish them with your fingers. So this is one of the main types of embryos you get. Also frozen raindrops. So when there's deep convective storms, raindrops can be lofted to very high altitudes, to temperatures well below 0 degrees Celsius. Eventually they will freeze. And when they freeze, they can serve as an embryo. But really what we need is something that's sort of on the order of millimeter to centimeter in dimension. The idea is that it's a particle that's much bigger than those supercooled drops, so it has an appreciable fall speed difference from those supercooled cloud droplets, and can lead to collisions and then thus collecting and growing the hailstone. But really, it's kind of fun to think about. Any particle really that's of this size or so can actually collect supercooled droplets in the storm. And so there's this great example from Johnny Goodson that had this picture posted online. So I reached out and gave me permission to use it. But this is actually a piece of a corn stalk that was ripped up from a field that had just been plowed by a tornado and sort of swept into the storm. And it's a particle that's several centimeters wide, so it's much bigger than those cloud droplets. And so it made it up to the hail growth region. And you see this ice accumulating on it. It's actually became sort of its own sort of hailstone. So any particle up there in the cloud that's big enough can serve as a collector particle. And then finally, once you have those first three ingredients, which are definitely necessary to get hail, you need residence time. So this is kind of like how you bake it in the oven, right? You need to have the airflow trajectories in the cloud, the three-dimensional airflow patterns, take that hailstone and guide it through the cloud to stay in the updraft where that growth is happening. And the longer it can stay, the larger it can grow. So we're going to be talking a lot about trajectories in this talk, and so we'll be coming back to that here soon. So when a hailstone is growing, one of the things we need to take accounting of quantitatively in our models is the surface energy balance. So if you remember back in your cloud physics class, when you have freezing of liquid water, right, there's an energetics that's associated with that. So the enthalpy of freezing actually serves to increase the temperature of the hailstone surface. So that sort of excess energy is put on the hailstone surface. And so that's kind of color-coded in red here. That's going to be leading to a temperature gradient wherein the hailstone surface is warmer than the environment. And so that's going to set up thermal energy transfer to the environment through conduction, but actually mainly forced convection. And so you've got that on the other side of the equation. But also, I put sublimation here. It could be sort of depositional growth or sublimation, but oftentimes because that hailstone surface is at a higher temperature than the surroundings, you might actually get sublimation happening even as the hailstone is growing. And then finally, the warming of collected liquid and ice. And so if you imagine that this hailstone is warmer than its surroundings, when a supercooled cloud droplet, or maybe even a ice crystal comes in contact with it, that supercooled droplet or ice crystal is going to be at a lower temperature than the hailstone surface. And so there's going to be an energy transfer to warm up that collected liquid and ice. And so kind of as a cartoon here to kind of show one of the interesting things that can happen in growing hailstones. So imagine that we're at somewhere in the clouds at air temperatures, maybe say minus 20 degrees Celsius. And so if we have our hailstone here, here's like a digital thermometer, also minus 20 degrees Celsius. So as the cloud droplets are being swept out by this hailstone and begin to make contact and freeze, that enthalpy of freezing is going to warm up the surface of the hailstone. If that excess thermal energy cannot be dissipated to the environment fast enough, you can actually raise the surface temperature of that hailstone up to 0 degrees, at which point we say it enters the wet growth limit or the wet growth regime. So now, if the surface of the hailstone is at 0 Celsius, as it collects supercooled liquid drops, those drops may not freeze right away, and you can actually lead to sort of liquid layers on the surface. So we call the surface wet in that case, and that's what we call wet growth. So this only happens when that surface temperature reaches 0 degrees Celsius. Otherwise, we call it dry growth. So why is those sort of growth regimes important? Well, one of the classic and characteristics features of hailstones are these onion-like layers that we see. So this is a thin slice of a hailstone observed in Australia by my collaborator, Dr. Joshua Soderholm. And it has the classic ring-like structure that we all kind of know and love about hail. And so these different layers actually tell us something about those growth conditions. So for example, these milky layers, these kind of cloudy white layers that you see, those are what we would call dry growth layers. They're cloudy because we've got lots of trapped air bubbles and sort of little facets from where those liquid drops have frozen in almost instantly on contact. And multiple scattering from all those different surfaces leads to the white appearance, much like clouds or a glass of milk is white. Now, these other layers that you see, it's backlit by a sort of, well, there's a black fabric beneath this. And so the dark layers are actually transparent or translucent. And those clear layers are what we see as signs of wet growth, where the surface temperature rose to 0 degrees Celsius, any air that was trapped in the liquid can actually escape. And so it leads to a much clearer ice. You don't have all those little nooks and crannies to scatter the light. And so by studying the rings of the hailstone, we can tell something about the growth conditions. And if you look at, say, the center of this particular hailstone, you can see the sort of central collector particle or the embryo that served as the nucleus for growth in this case. Okay, so when we are considering all these ingredients coming together, a lot of our work is going to be based on supercell storms. And that's because supercells bring together those ingredients in quite favorable ways. So there's a video here that'll be playing as a time lapse of an aircraft flying near a supercell from V-Speed, courtesy of Joe Pica. But a couple of factors about supercells that makes them really conducive to hail formation. First, they tend to have broader updrafts that are less affected by environmental entrainment. That means you get pretty close to adiabatic liquid water content inside the updraft. So you've got lots of supercooled liquid drops available. Supercell storms tend to have very strong updrafts, and so that's another one of the key ingredients. The interesting dynamics of supercells actually means that they have a propagation that's sort of off the mean flow. And that allows there to be storm relative winds at most layers throughout the supercell, throughout the depth of the storm. And that's really helpful for getting embryos to be swept in and placed in that optimal growth region. And then finally, the trajectories that we're going to talk about, the mesocyclone of the supercell actually helps to guide those hailstones across pathways that allow them to stay in the updraft for long periods of time to increase that residence time. And so the supercell storms are really going to be the best, most favorable types of deep convective storms to produce hail. And the proof is in the pudding. If you look at all the different sort of hail reports that we have out there, supercell storms are responsible for over 90% of what we would call significantly severe or greater than 5 centimeter sized hail, 99% of the giant hail greater than 10 centimeters, and then 100% of the new category gargantuan greater than 15 centimeter hail that we came up with. So really, if you're talking about the high end, the most impactful, the largest, and most potentially damaging hail, that's going to be the supercell storms that produce that. So our group, and for this talk, we'll be focusing on supercells for now. I have a new student who's going to be branching out a little bit, but that's work to be down the road. So for this talk, we'll be mainly focusing on supercell storms. So the methods, in the title I said we're using models and observations. And so the first part of this talk is going to be talking about the numerical models that we use. So why do we want to use numerical models? Well, it's really nice to be able to create a hailstorm on the computer. We can control everything we want about it and systematically explore the environments and how those environments may affect the hail production. So we can turn the crank on those environmental controls like cape and shear. And what out comes in the model, we get a hailstorm that we can then use to analyze for the dynamics and the microphysics and how the hail is produced in that particular storm and how it might vary if you try to vary the environment. So the specifics here, for those of you who are interested, we're using Cloud Model 1, CM1. It's an idealized numerical model. It's a model that's used for idealized studies. It's by George Bryan out at NCAR. Most of what we're showing today is going to be grid spacings, horizontal grid spacings of about 500 meters, vertical grid spacings of 250 meters. So it's a storm scale simulation. We have done some sensitivity down to even finer grid spacings, and the results don't change. So this is mainly for the computational expense to kind of keep things manageable. Pretty large domain. The domains are going to be moving with the storm, so everything we show is going to be in a storm relative framework. If you're interested in the conditions, we use free slip lower boundary, no PBL scheme, no radiation, open radiative lateral boundary conditions. And the Morrison two-moment microphysics is used for the CM1 simulation. So if you're kind of aware of microphysics schemes, you might be wondering, oh, wait a second, how are you going to study all these things about hailstones if you're using a bulk microphysics scheme? These bulk microphysics schemes do not predict every individual hailstone, so it's going to be really tough to look at hailstone trajectories from a bulk microphysics scheme. So instead, we use a model that we developed here at Penn State, the hail growth trajectory model. It's described in detail in our 2020 JAS paper if you're interested, but I'll give a couple of basics here. It's a fully Lagrangian trajectory model. And so what we mean by that is that it's not going to be sort of stuck to the different grid spacings or different grid boxes. So the trajectories of the hailstones are going to be smooth and they can go throughout that entire domain. And it's driven by the CM1 simulated flow fields. So we're creating a storm with CM1, and then we put in this trajectory model to then simulate the hailstone trajectories. We initialize those hailstone trajectories using on the order of 100,000 embryos, varying initial sizes. We place them pretty much everywhere in and around the main updraft of the storm. And that's done at every output time or every sort of composite time that we want to do. So we have a lot of flexibility. It's offline. These calculations are done offline, which means that we can go back and change things and study the sensitivity, which is nice. And so we account for all of the explicit microphysical processes that are thought to be important for hail growth from the CM1 simulated fields. So I'll just put the list of these up for those who are gurus of microphysics and interested in this stuff, but the main source of growth is the collection of supercooled cloud droplets and raindrops. We use continuous collection. We have a kind of a special parameterization for cloud droplet collection efficiency. We're using variable Rime density, following some of the previous work by Andy Hamesfield and collaborators. We do have collection of ice crystals and snow, but that's only during wet growth. The physical sort of interpretation behind that being that if the surface of the hailstone is wet, it's going to be much easier to have an ice crystal then sort of come in and be incorporated into the mass than if the hailstone surface is dry. We include sublimation and deposition. If the hailstone density is less than solid ice, we can actually soak the liquid into the nooks and crannies that are formed by the sort of air pockets that we talked about earlier. It includes shedding, and it includes the sort of Reynolds number dependent thermal energy and vapor transfer coefficients to help modulate that thermal energy transfer to and from the environment. And if you're wondering, yes, we do get rings in our model as well. So we can simulate those hailstone rings. And so we'll be revisiting that towards the end of the talk. Okay, and right before the results, I just wanted to show also a quick refresher on hodographs, because I'll be showing a lot of hodographs in this talk. So a hodograph is a way that we can map out the vertical wind profile. The vertical wind profile is one of the main things that we've been tweaking because we have reason to believe that that's going to have a significant control on the storm's ability to produce hail. So the way we map it out in this parameter space, the x-axis represents the U, or the zonal east to west wind component, and the y-axis represents the V, or the north-south meridional wind component. And so you can draw your wind vector. Say here's the surface wind at every height. I'm showing it here in every 1 kilometer layers. So you have surface 1K, 2 kilometer, 3 kilometer, et cetera, up to 6 kilometers. So we trace out the wind vectors at every height. And it's nice in this graphical format because the distance or the separation between these two vectors gives us the shear vector. So for example, this green arrow that you see tracing between 3 and 6 kilometers traces out our 3 to 6 kilometer shear vector. So the hodograph basically connects the tips of these vectors together and makes a nice little shape kind of like this. So this is what we would consider like a quarter circle turning hodograph where the winds are turning with height, and you can see the shear. Now, the supercells, like I said before, the dynamics makes them kind of interesting. They propagate off the mean wind, and so you may have a supercell storm motion vector that looks something like this, kind of away from the mean wind, to the right of the mean wind in the northern hemisphere. So if we mark that with a star, we can also then take the entire axes and shift it or subtract out that storm motion and put the storm motion at the origin. And then that gives us our storm relative wind profile. And so what you'll be seeing a lot in this talk is the storm relative wind profiles. We like using the storm relative framework because that's what the storm experiences. I like to give the example in class. If you're driving down the highway on a calm day and you stick your face out the window, you're going to feel 60-mile-per-hour winds or so hitting your face, right? It's not that the ground relative wind is 60, it's just that you're in the car and your car relative winds are 60 coming at your face. Right, so in this particular case, you'll see that the storm relative winds can be found by drawing a vector from the origin to the hodograph. So at the surface, it looks like we have winds basically out of the east, and then they turn with height following that outlined hodograph. Okay, so let's dive into the first set of experiments, which we looked at the vertical wind shear. So here's a set of the hodographs that we use, the storm relative hodographs. And the black dots are showing the 0 to 3 kilometer wind, the blue dots are 3 to 6, and then pink is above 6. And really the thing that I want to point out is that as you go from blue to gray to green to gold to pink, these boxes, the outlines, that's indicating increasing deep layer shear. And you can kind of see how this horizontal part of the hodograph is getting longer and longer as you move through those colors. So keep those colors in mind because that's going to be the sort of color coding that we'll use for the next several slides. So what happens if we simulate all these storms, we put all these embryos in, simulate hundreds of thousands of hail trajectories, and take a look at the bulk statistics about hail production in each of these? How does vertical wind shear in this particular framework affect the hail production? So here is the results. On the x-axis is the hailstone diameter, and this is basically like a histogram. It's a log scale on the y-axis. And this is the number of those initial embryos that's resulting in a given final size. So you can see a lot of these kind of almost linear for a good portion of the space in the log scale. So it's basically an exponential type of size distribution. And really what stands out is for these larger hailstone sizes, as you increase the deep layer shear, so as you go from the blue to gray to green to gold to pink, we see both larger hailstones as well as larger concentrations of those larger hailstones. And so we found in this case that the increased deep layer shear led to greater amounts of hail and larger sized hail. So what's going on? So we wanted to dig into those ingredients and see what was causing the greater hail production as we increase wind shear. So first we just looked at the updraft. This is the maximum updraft speed. I've highlighted here between about 4 and 8 kilometers is approximately the hail growth region. And you can see that most of it, the lines are all on top of each other. These are the maximum updrafts in each of these different wind shear cases. So it's really not the maximum updraft speed that's doing much. Instead, if we look at the updraft volume, this is really where we start to see some statistically significant differences. And so as you go from blue to gray to green to yellow to pink, increasing the wind shear, we see that have an increase in the volume or an increase in the updraft width at those altitudes in the hail growth region. So what's going on with that? Why does increasing the wind shear lead to greater updraft widths? So think about our storm relative hodograph. Here's our storm motion. So our storm relative wind at low levels might look something like this for this little cartoon that I've drawn. If we increase that deep layer shear, pull this part of the hodograph out, we actually tend to bring the storm motion further out. And I'll flip back and forth so you can see the difference in the sort of magnitudes of those low level storm relative winds. And we see that increasing the deep layer shear tends to increase the low level storm relative winds. And there's been a handful of studies that have recently looked into this, and John Peters' recent paper in JAZ is a great one to take a look at. But the greater low level storm relative winds implies a greater inflow into the storm and greater updraft width. And so the current thinking is basically for some amount of buoyancy, if you're just basically shoving more air into the storm, it responds by having a wider updraft. So it's basically a mass conservation type of argument. So when we increase shear, we're increasing the updraft width. So why does increasing the updraft width lead to larger hail? So if we think about it, there's basically two possibilities here. One, you could have longer residence time along those trajectories, or two, you could have larger growth rates along those trajectories as well. So I want to just show on the left plot here, this is sort of some of these trajectories. The cyclonically curved turquoise lines here are showing what these trajectories look like when projected onto a plan view. The pink outline is the updraft. You can see that they're cyclonically curved. They start with this little grid of embryos here. And they follow this trajectory when projected down onto the surface because of the mesocyclone. This animation shows the same kind of thing. Here's a three-dimensional view of a trajectory like that. The green outline on the surface is that projection. So you can kind of see these cyclonically curved trajectories as the hailstone is taken around by the mesocyclone. So let's examine just this first bullet point for now, the longer residence time along these trajectories. So if we imagine our updraft viewed from above, this is a plan view of our updraft with our typical hailstone trajectory going through it. Simple idea might say, well, if we increase the updraft width, we might be able to basically have a longer trajectory that's in the updraft and longer residence time. So it turns out that that's actually true. Increased updraft area increases the distance traveled or the path length that the hailstones can take across the updraft. And so wider updrafts lead to longer residence time. So here on this plot is again showing a kind of a histogram with residence time now on the x-axis, residence time within the 10 meter per second updraft, and then the count. And you can see going from blue to gray to green to yellow to pink, we have this tendency for increased residence times because of the longer possible path lengths that the hailstones can take. Okay, so then we're like, okay, well, that was the deep layer shear. Let's crank up the low level shear. So for the next set of experiments, we basically increase this low level meridional 0 to 2 kilometer winds, effectively increasing the low level shear. So the photographs get kind of elongated in this north to south direction. So here's what they look like, the storm relative photographs for this set of experiments. And to our surprise, when we went through and did the hail sizes, just showing two of them here, the extreme cases of the solid line being the weakest low level shear and this dotted line being the strongest low level shear. You notice that the dotted line is sort of falling below the solid line. That's implying that increasing the low level shear actually leads to smaller hail sizes and fewer of those stones. So sort of a counter to what we just saw about the deep layer shear. So what's going on here? Well, we take a look at our updrafts. The solid lines are showing those original set from before, and then the dashed lines here are those with the greater low level shear. We still get increasing updraft width. So something else must be going on. We increase the low level shear, we still get larger updrafts, but somehow we're not getting the larger hailstone sizes. So if we look at the residence time next, and again, the dotted lines represent these cases with the greater low level shear, you see that there's a tendency for smaller or shorter residence times, even though the updraft width is getting wider. Right? So you scratch your head, okay, what's going on? Well, let's go back to basics. What affects the residence time? Right? Time is the distance traveled divided by the speed. So the distance traveled is that path length the hailstones take across the updraft. And the speed is obviously the speed at which they're being advected by the winds across the updraft along our trajectory. And so again, if we have our top-down view of our hailstone trajectory here, right, the part of the trajectory that we're most interested in is this sort of west to east part and then this south to north part. So we broke down the wind components, the horizontal wind components in the updraft, the U and the V, to see what they look like. So here's the average westerly winds in the updraft. The solid lines are from the case of weak low-level shear, and the dotted lines are the ones from the stronger low-level shear. And there's maybe a bit of a separation, but you can see that a lot of the lines are kind of overlapped, right? So the statistical significance isn't so great with those. If we look at the southerly wind, so this portion of the trajectory, we see a huge difference, right? Now we have a total separation in the hail growth region between that case of greater low-level shear and weaker low-level shear. Right, so the greater southerly flow within the updraft seems to be affecting the hailstones faster. And so even though the updraft's bigger, they're being whisked around faster by that stronger flow, and thus their residence time goes down, and thus their sizes goes down. And so what's happening here, I'll flip back and forth. By increasing that kind of low-level north to south part, we're sort of enlarging the mid-level storm relative wind magnitude. And it may not be immediately evident why that's important now, but we're going to get into that in a little bit. The increased southerly storm relative winds ultimately leads to increased southerly in updraft winds, and thus the faster hailstone advection and the smaller residence time. So take a deep breath. So far, we did these vertical wind shear experiments. In the summary so far, we found increased deep layer shear when we elongated the photographs in that zonal direction, increased the hail production because of the bigger updrafts. But when we increased the low level shear, we decreased the hail production because of that faster advection across the updraft. So I just wanted to pause and say one thing about this. I usually get this question. We're talking about zonal and meridional. The photographs that we used were such that the sort of deep layer shear was mainly zonal. We use that because that's kind of like the average, but really the way to think about this is you can have these photographs in any sort of direction, any flow pattern. You can flip them upside down to be in the southern hemisphere. And so the idea is that the increase in the deep layer shear, whichever direction that is, and then the increase in the low level shear being orthogonal to that deep layer shear vector. So sort of a little nuance about these results. Okay, so recently my PhD student Yuju looked at some instability controls. So the amount of environmental instability, or CAPE, how does that affect hail production? And so the first set of experiments did this for a fixed wind shear profile. So we held everything else the same and we just changed the amount of instability, with the expectation that a stronger updraft would result from increased instability. So basically we're turning up the crank. In this plot here, the colors going from this gold to purple increase is indicating an increase in CAPE. So these values are the amount of CAPE in the environment in joules per kilogram. So from 1800 up to 3000. This plot shows the basically like a bar chart or a histogram of the final hail size greater than what's listed and the count. So the idea being, if you pick a size, say like 25 millimeters, this is how many of those initial embryos exceeded this particular final size. And so as you might expect, as you start to ramp up the instability and ramp up the updraft and speed, you get an increase in the amount of hail produced at given sizes. But then interestingly, we kind of get this wiggly pattern after that. So it's not a monotonic increase. We actually sort of get this optimum at mid-range CAPE values, and then be a secondary peak here a little bit higher up. So there's this kind of interesting non-monotonic behavior that's going on. Briefly, I want to show that Yuju went through and actually looked at how these results changed if you also look at the vertical wind shear. So on this left column is different values of that deep layer wind shear vector, which is similar to the values that we saw before. So as you go from the top to bottom, we're increasing our deep layer shear vector. And what's shown in each of these panels is how the different hail sizes, residence time, actually, and also liquid water content are varying as a function of CAPE. She's normalized them to z-score just so we can fit everything on the same y-axis. But the idea here is where you see the peak, that's where you're seeing your largest hail sizes, your largest residence time, and your largest liquid water content. On the right column, it's how we distribute that CAPE. And so for any of the forecasting gurus, if you put the maximum buoyancy level at lower altitudes, you get sort of what's called a fatter CAPE profile. Whereas if you move that up to the higher heights, so this is the maximum buoyancy height at 8 kilometers versus 6.5, you get skinnier CAPE. And just the point that I want you to take away from this is that optimum CAPE value, where we get the largest hail sizes, actually shifts whether we change the vertical wind shear or whether we change the placement of that level of maximum buoyancy. So it's not just like there's one magical CAPE value, it depends on the other factors in the environment as well. So we want to look at the residence time. How do these changes in instability affect residence time? That's one of our key ingredients for hail growth. So I'll put the equation up here just as a reminder, right? So the time is equal to the distance divided by the speed. So as a function of CAPE, here's the updraft area. We see a pretty solid increase in updraft area with increase in CAPE. And so increased CAPE means wider updrafts. If you increase the path length that's possible, you'd increase the residence time. So all else being equal, that should contribute to increased hail sizes. When we look at that south to north component of the wind speed in the updraft, that special one that we saw a big difference in from that previous study, we also see an increase with CAPE. So increased CAPE also means faster motion across the updraft. And that's on the denominator. So if we increase the denominator, that's going to contribute to a decrease in residence time. So it turns out we have these competing effects of increased CAPE making broader updrafts, but then also faster advection across it. And that's why we end up with these local peaks or local optimum points relative maxima in the hail production. So what's really affecting that southerly flow? That seems like an important factor that we've seen both in the wind shear experiments and in these instability experiments. So we're going to take a little bit of a dive into the storm dynamics here to try to explain this. So what's shown on the left here is the 4-panel plot showing a horizontal slice at mid levels within the hail growth region. of the pressure perturbations. That's the shading. So the blue is negative pressure perturbation, red is positive pressure perturbation. The yellow is outlining the updraft at this level, and these pink vectors are showing the two-dimensional wind flow at this particular level too. So here's a total pressure perturbation. This is pretty common in supercells where you, on the upwind side of the storm, you have a large positive pressure perturbation. You can see the streamlines would be diverging away here. It's just necessitated to have a high pressure perturbation there then to be associated with that. And then down here on the sort of southern or right flank of the supercell, we get a negative pressure perturbation. If we break it down, try to figure out which component is contributing the most to this. This is the buoyancy pressure perturbation. This is the nonlinear dynamic, so spin or splat, if you are familiar with those terms associated with the flow field, deformation and vorticity of the flow field. And then the linear dynamic, which is the sort of updraft and shear component to the pressure perturbations. And really what you see is that the nonlinear dynamic pressure perturbation is what's dominating this total here. So the presence of vorticity associated with mesocyclone and the presence of deformation associated with the flow diverging around the updraft at mid levels is really what's sort of governing what this pressure perturbation field looks like. So why do we care about this pressure perturbation? If you imagine parcels of air that are entering the updraft will be coming from the environment and then ascending in the updraft. And so those parcels, if we ignore friction on these scales, we can ignore Coriolis. Those parcels will be governed by gravity, buoyancy, and pressure perturbations, the pressure gradient accelerations that they might experience. And so what we wanted to do is say, okay, if we're concerned mostly with this south and north component, this part that guides the trajectories across the updraft, let's just look at that south and north component, so the meridional component of the flow. And we're going to concern ourselves with only that component just for simplicity right now. So you can imagine our storm. And if we imagine an air parcel, here's a little kitty and a pumpkin for Halloween, it's coming up in 2 weeks. If we imagine just the component that's going from south to north, as that kitty and the pumpkin approaches the updraft, right, we see it's under the influence of this pressure perturbation, this minimum pressure perturbation. It's going to be experiencing a pressure gradient acceleration towards the updraft. Once it starts to ascend in the updraft, however, right, eventually it may pass through that pressure perturbation and find itself on the other side. When it's got a low pressure behind it, that means it's facing an adverse pressure gradient acceleration. It will begin to decelerate. So the hypothesis here is that the sort of interplay between that pressure perturbation magnitude, the flow of the parcel that's entering the updraft and how fast it goes up the updraft might have something to do with the flow that we end up getting in the updraft. So we did some parcel composites here of a bunch of parcels in the inflow to try to see what this looks like. So this top panel shows the meridional pressure gradient, dp dy, as a function of time. And these different colors are like before, they're showing the different Cape values. And so one thing you see that they're all negative at first. That means that the parcel would be accelerating towards the north. The bottom panel shows that parcel's V component or meridional component to the flow. And again, you see that they're all increasing in time in the beginning, which means they're accelerating to the north. Now, these red circles that you see are where the parcels are entering the updraft. Sorry, the parcels are entering the hail growth region of the updraft and then exiting the hail growth region of the updraft. So we're really concerned with between those two red circle markers, that's going to be where the air is actually in the hail growth region. And so what do we see? Well, with Cape, we see larger pressure perturbation magnitudes. So increased Cape leads to larger pressure perturbation magnitudes. We also see that the increased Cape means that your parcels are already starting out with greater meridional flow speed. So they're starting out with greater momentum in that direction because of the way that the storm motion changes with Cape. At some point after they enter the hail growth region, you see that the pressure perturbation or the pressure gradient acceleration changes sign, which means that they're starting to decelerate. But what you also notice, right, is that for the purple line, we have sort of the point in which it exits the hail growth region is actually earlier than as we move to these lower Cape simulations. And so the idea here is that those higher Cape simulations, the parcels have greater momentum as they are moving and accelerating towards the updraft. They accelerate more. But then because greater Cape generally means larger or greater magnitude updrafts, the parcels are riding up that updraft faster and have less time to be decelerated once they pass through that pressure perturbation. And so that means that they retain a greater amount of that southerly flow in the updraft compared to the lower Cape simulations. So it's really a complex interplay of the starting momentum, how fast it descends in the updraft, and the and ultimately the strength of the pressure perturbation as well. So what we can summarize from this is that increasing Cape leads to non-monotonic changes in hail production owing to competing affecting residence time. And that complicated behavior is superposed on the trends associated with that background wind shear that I showed you in that one brief plot. So things are getting pretty complicated in terms of the environment, which means there's no surprise that the forecast parameters are not doing a particularly good job at picking out these nuances. Also wanted to mention one thing about the larger growth rates. We kind of ignored this part for now, mainly we talked about residence time. But let's take a look at some of these growth rates. So hailstones will grow primarily from collection of supercooled liquid cloud droplets. And the amount of liquid water that is available to them is based on the amount of water vapor in the environment, minus fallout and entrainment, right? So if you just assume parcel theory, right, it's based on how much water vapor is present in the environment. So the question becomes, well, which air parcels are participating in that mid-level updraft where the hail is actually growing? So we wanted to answer this question. So here's another picture of a horizontal slice of the updraft. And we put a bunch of passive tracers throughout the lower troposphere in the inflow sector to see where they would end up. And what it turns out, these are color coded here. So going from blues to the warmer colors means starting at the lowest altitudes and then moving up through the lower troposphere. You can see that these are actually nicely separated. These contours are representing the amount of those passive tracers that's found at mid-levels in the updraft after they've been swept into the updraft. And we get this nice separation where the lowest level air is actually kind of on this left side of the updraft, and it gradually, as we move across the updraft, we're getting parcels that originate from slightly higher portions of the inflow. Now, interestingly, if you think about what your storm relative photograph looks like, and I've color coded these the same way, you see the same type of left to right changes in the colors, right? So the idea is that the distribution of where the low level air originates, that distribution across the updraft, is dictated by the environment. And that's pretty complicated. We don't have any forecasting parameters right now that account for that. And further, I'll just kind of remind you of what these trajectories look like. It's oftentimes on the right edge of the updraft. So something like this region of the updraft here. And so you notice that the air from this region is actually in the sort of 1.5 to 3 kilometer altitude. Most of the hail parameters that have been used so far for forecasting are looking at surface-based parcels or the 100 millibar mixed layer near the surface. And so that air may not actually even be relevant for the hail. So it's something that we have some colleagues that are looking into right now. So summary for this a little bit. Liquid water content is available not just from the surface, but it's throughout that depth of the inflow layer, and in particular, perhaps even the upper portion of that. And its distribution across the updraft is modulated by the environment. So a lot of complexities just with the little bit of parameter space that we looked at. Is the background environment the only control on hail production, however? And unfortunately, for that, the answer is no, even though we think we have enough complexities as is. So I wanted to show just briefly what happens if we have a static, homogeneous background environment and we allow the storm to evolve freely, and we put in embryos every 30 seconds and just let them go. So this is a three-dimensional view of the sort of little segments of the trajectory every 30 seconds, colored by the time of embryo insertion. The green is the simulated near surface reflectivity, and the red dots are showing where only the severe hailstones are falling out. And what may strike you is that they are following similar pathways, but you notice that there are gaps when there are certain times when embryos don't create large hail. Again, nothing in the environment is changing. This is just purely the storm's life cycle, the storm's behavior. So I wanted to show just briefly some output metrics, hail size metrics. And so in particular, pay attention to these pinks and blues. These are the larger hail sizes simulated from this particular simulation we had. And over the life cycle of the storm, again, for a constant background environment, we see that the max size can more than double on short timescales, less than 20 minutes. Further, the number of severe stones produced by those initial embryo seeds can vary by 1 to 2 orders of magnitude over that life cycle. So there's a lot of interesting evolution that's happening just because of internal storm dynamics. So I know I'm running short on time, so I'll go a little bit quicker here. So what's going on? If we look at the ingredients, we looked at the larger hail times shown in this kind of light blue. Dark blue is smaller hail time, and the gray is the smallest hail time. These are 95% confidence intervals about those times. Sure, there's a little bit of increased super cold liquid water content, but it's only about 10%. So we didn't think that was really the greatest factor. If we look at the updrafts, here's the mean updraft profile, 95th percentile updraft profile, and then the updraft area. We do see a pretty big separation now, right? The larger hail production occurs at times of weaker and wider updrafts. We look at our two favorite horizontal wind components, not much of a difference in U, but we see a huge difference in V. So the times of larger hail, it's weaker updrafts, wider updrafts, and we're seeing a slowing of that south to north advection speed. So we looked at a bunch of different storm attributes. This is showing a corner plot, as we say. So it's basically correlations between all these different storm attributes that we think might be important for hail growth, colored by the number of severe hailstones that they produce. There's a lot to look at, but basically I wanted to highlight a few. Mean southerly flow versus mean updraft speed. Those two parameters are not correlated themselves, but you notice that the bright points here are shown on the bottom left, which means weaker southerly flow and weaker mean updrafts. Further, if we look at 95th percentile speed and updraft area, we see that the brightest points are up at the top left. That's indicating weaker updrafts and wider updrafts. So we're really seeing the signal coming through strongly in these simulations. So what's going on in the actual storm dynamics in this case? So we composited a few minutes of when there was large hail being produced. This is a horizontal slice. You see the updraft in pink, simulated reflectivity in the color, and here are the airflow patterns. And this is the small hail times. These small hail times are actually shown or come from a few minutes before the large hail time. And we can take the difference to really try to see what's different about the storm structures. So a few things that jump out. You see the difference vectors are pointing south. That means that there are weaker southerly south to north winds at the large hail times when you take large hail and subtract off these stronger small hail times. And then probably what jumps out the most to you is this sort of anticyclonic vortex here that you see at the small hail times. It's not there at the large hail times. So what happens is this actually is being advected off to the north in this case. And so we call it shedding of anticyclonic vortices. Sometimes you see this associated with storm splitting. When that happens, the updraft expands and weakens. And so this is something that we think is maybe important to producing larger hail. When you look at the hail swaths from this, I think Ralph was talking about this before the seminar started, the really tight gradients, both in size and concentration. And I'll just leave you with this thought about this, that do hail reports accurately portray a storm's hail production? If your town is here, right, you may not be seeing where these maximum sizes are being produced. And that's going to really make the challenges for these types of studies that are trying to pair up environmental factors to the ultimate hail sizes that are produced. So finally, in the last minute or two here, I just want to share some of these new observations that we're really excited about. A lot of this is a little more work in progress. But recently, there's been an advent of 3D infrared laser scanning, where we can actually digitally map out the three-dimensional surface of hailstones. So these are actual real hailstones, even though they look like goldfish or stegosauruses or something. And we can use these digital models for a whole host of different purposes. So put a few of them up here, but for instance, we can compare the equivalent spherical volume diameter to the maximum dimension. Oftentimes in our models, we're treating spherical hailstones. And so here's a way to sort of map what the true lobe irregular shapes are to the equivalent volume spherical diameters. Also, you notice we can look at the surface area enhancement, or the inverse of sphericity, which basically shows how irregular that surface is. And this is going to be important for things like thermal energy transfer, which is proportional to the surface area. So if you have more surface area than would be accounted for in your models, it's going to be a greater thermal energy transfer available from that. I'll just put a shout out that Yuju, my PhD student, is actually working on incorporating all of these into model microphysics parameterizations right now. All these different factors are interconnected and it's non-trivial, but she's doing some great work, and it's going to be presenting about this next week, actually, at the Severe Storms Conference. We're also interested in radar. I'm a radar person by training. So here's showing the hailstone maximum dimension versus the S-band reflectivity factor for one of these hailstones per cubic meter. Each of these colored sort of blobs is showing one of these hailstone models, rotated 770 different orientations, and we calculate the scattering. The white circle and bar represents the average, and then the 10th and 90th percentile. And really the take-home point here is that most of our models, most of our radar algorithms are based on spheres or spheroids, which is given by this pink curve. And the variability that we get from real hailstones is far greater than what we're currently accounting for in our algorithms. And this is going to help. This is really going to be challenging for our algorithms to try to take care of. So we're working on a study about this right now. Joshua Soderholm, who had that beautiful hailstone thin slice that you saw earlier, he did some great work in actually automating computer vision analysis of those growth layers. And so we're for the first time getting some bulk statistics about, say, the wet growth fraction. So what percentage of the hailstone was grown in wet growth versus dry growth? And these are types of things that I'm very excited about, because this is now allowing for the evaluation of our models, not just in terms of the sizes produced, but at the process level. Are we getting our processes correct? So for example, here's a collection of his observed hailstones that have been converted into our sort of model spherical shapes, where the white shows dry growth and the gray shows wet growth. On the right side is our simulated hailstones, randomly selected for the same population of sizes. And what immediately should stick out to you is you see a lot more gray on the right than you do on the left. So even though we can reproduce the same sizes, we're seeing a strong bias towards wet growth in our simulations. And so our leading hypothesis right now is that it's about the treatment of the energy coefficients. And you can ask me about that later if you're interested, but we're working on that currently. So I know I'm out of time, so I'm just going to put all of the summary bullet points up here. Thank you for your patience and thank you for your time. If there is any time, I'll be happy to answer any questions.
All right. Thank you, Matt. This is a great talk. This now is our Q&A session. So please feel free to unmute yourself and ask a question. You can also chat us. And okay, we do have an early question from the chat, it's from Jenny, and she said, she or he said, this is a general question, but can you comment on what determines the shapes of the hailstone, which appears to be quite random?
Yes, that's an excellent question. So, yeah, short answer, we don't really know. So there are some ideas about the general shapes having to do with the falling behavior. So whether the hailstone is sort of processing about some fixed axis, or if it's randomly tumbling, you can imagine if it's randomly tumbling, each of the surfaces, each of the side of the surfaces will be exposed to the airflow and can grow roughly symmetrically. But if it's instead got some sort of wobble or spin, then certain areas, certain faces will be exposed to the flow more and will grow faster. There's also the lobes, and there's really pointy ones are called icicle lobes, and they're thought to grow much the same way as icicles do, except instead of dripping down, maybe being either centrifuged out or being sheared off the backside. And the complexities you can see can arise when you start to grow a lobe. It's going to destabilize its orientation. If it did have a stable orientation, it can start different fall behavior. Different fall behavior will feed back into how it grows. So really, we've seen a pretty rich diversity of natural shapes. The one paper that one of my former undergraduate students worked on, Laura Shedd's paper, and I'll show you a picture right here. She did go through and characterize several thousand hailstone shapes. And so we do see some preferred areas of the sort of aspect ratio parameter space that result from that sort of bulk statistics, but certainly, you could almost say that each hailstone is unique, just like a snow, just because there's such stochasticity involved in its growth and falling behaviors.
Okay, thanks. And any other questions? Okay, maybe I can take the privilege to ask a question. So I'm a remote sensing guy, and can you talk about like how can we verify the hailstone, the hails using either passive or active remote sensing microwave?
Yeah, really great question. So I think so that that one picture I just showed, we actually are putting together a book chapter on radar remote sensing, so active remote sensing of hail, and the detection of hail, I think, is fairly well established. Even simple methods like looking at the low level reflectivity factor, if you're allowing for some misses once it passes a certain threshold, pretty good indication that you've got hail there. There are also storm integrated techniques, things like the maximum estimated size of hail, that are really good at detection. From satellite, passive microwave, I know there've been some really good work by Dan Cecil, Sarah Bang, and others who are looking at basically proxies about the brightness temperatures that are showing high probabilities of hail being present at the surface. So I think from the detection standpoint, we have a lot of really great tools, both from satellite and radar remote sensing. When it gets to the sizing or quantification of, say, amount of hail or hail size distributions, I think that's really where the challenges start to creep in. And in part because of the effect that you sort of see here, especially for the larger hail, it's way outside of the small particle scattering regime. And you can see, for example, everything from about 2 centimeters to 7 centimeters has the exact same backscattering cross section. And those bigger stones are always less, or in smaller number concentrations than the smaller stones. And so in terms of being able to directly detect them, I don't think you're going to be able to with either passive or active remote sensing. But I think there may be some proxies based on storm updraft and things that we're working on now that might be a little bit better. But so detection is great. Sizing, not so much.
Okay, thanks. And we have a couple of questions from the chat. First is from MH. So his question is, thanks for the very interesting talk. Can you please describe the magnitude of SLW and how to measure it generally?
Oh, great question. I'm assuming you mean supercooled liquid water. And so there's, let's see, we have this is the one sort of plot that has some of the numbers on it from our simulation. So this is from the model simulation. This is the mixing ratio of updraft cloud liquid water content. So you can see that within the 15 meter per second updraft, the mean value is something like 2 to 3 to 4 grams per kilogram. Rain liquid water content also can contribute, but we're not quite sure exactly what the efficiency of collection would be for those raindrops. In terms of how to measure, that is a super challenging question. Right, you could take parcel theory, adiabatic water content, but that's ignoring entrainment, fallout, things like that are going to be tough to quantify. So in the absence of aircraft penetrations, which happened back in the 70s and 80s, right now I don't have a good feel for ways to do that. So there's some proposed measurements using remote sort of systems that might do a better job of that. And sorry, road systems, I mean, releasing probes that then can be taken in situ through the storm that are being planned for the proposed field project called Ice Chip that we're hoping to get funded. But yeah, without those direct measurements, it's really tough. So we're kind of at the mercy of, do our models represent the cloud liquid water content well enough? And that is a very challenging question.
Thanks. And another question from Steve Nang. Have you looked at how your hail model results compare to the bulk microphysics?
Yeah, great question. So this work kind of originated actually in 2017 when we used the bulk microphysics scheme to not only drive the trajectory fields, but actually to look at the resulting hail mass that was produced. And so we actually tried to do something with the size distribution, but the reviewers said, no, you can't do that. It's a bulk scheme. So you can only look at the integrated quantities. So when we looked at the integrated quantities, we saw the same pattern, wherein if you increase the deep layer shear, we had an increase in the hail mass that was produced. And then when you increase the increase the low level shear, we saw a decrease in the hail mass produced. So at least in terms of the general amount of hail that was being produced, can't say anything about size, but the amount of hail, the mass of hail produced, the hail trajectory model and the bulk schemes are completely consistent. Further, our hail trajectories, a lot of the animations that I showed, I didn't say anything about it, but the bottom field that was shaded, I can get to it, is actually the bulk scheme's hail mass where it was predicted. Yeah. So really can't see much at all, but basically our hailstones are falling out where the bulk scheme says that the hail mass is falling out. So we've got some broad consistency in both the amount of hail being produced and then the region that it's falling out between our model and the bulk scheme.
Thanks. And any other questions? Okay, so while I'm talking, feel free to interrupt me with any questions. And just so you know that we have our next talk will be in 2 weeks from now. So please stay tuned. And in the meantime, we'll have our video recording uploaded on YouTube channel. It usually takes couple of days or so. I think with that, I will call it the end of the talk. And thank you, Professor, and let's thank the speaker again. And thank you.
Thank you very much.
Look forward to see you.
Thank you.
Thanks.